Welcome to my day 7 solution for the Advent of Code 2022 in Rust. So we got an easy problem yesterday, and it's been made up for today with a much harder problem. So rather than live walking you through it, like I like to do, because I have to think about then what I'm doing, why I'm doing it, and make sure I explain it properly, I'm just going to run through some of the highlights, show you how the solution comes together, because otherwise you're just going to be watching me type for like half an hour. I don't think that's useful to anyone. And then for part 2, we'll try and go back to the live coding, because that should be just a follow-on, I'm hoping. So let's talk about what's involved in this problem. We're working with the same communicator device that we were yesterday, and this time it's run out of memory. So we've been asked to find out where on the file system the memory is being used up most. So we start by being given a traversal of the file system, and we're going to calculate something like the disk-free command on Linux on top of that. So the output changes directory into every directory, walks through the whole file system, and does an ls in every directory to print out the children directories and also the size of the files that are in that directory. So that's our input, that's what we have to parse, and that in itself takes a fair bit of code. And then once we've done that, we're asked to find out the size of every directory. So working up the tree from the bottom, directories that don't have any subdirectories that are just containing files will have an obvious size because you just total up their file sizes inside that directory. But then as you work your way up the tree, the directories that contain lots of other directories will have the size of any files that are in them, plus the size of the child directories. So we've got to do a calculation back up the tree that we've just walked, and we're being asked to take all of those directories, calculate their sizes, work out which ones have at most 100,000 size, and then sum up all of those. So it's pointing out that there'll be some double counting, which is fine. So that's the problem we've got to solve. Let's jump in and start looking at the code. Alright, so I've started as usual by loading up the input file, which is just an extended version of what we've already seen. And then the parsing step is this first block of code here, which runs through each line and calls this process next command function. We'll look at that in a second. And then once we've got all of our content parsed, we know what directories contain what. We compute our child sizes. So that's doing a search through the directory structure and totaling up the sizes. And then finally, once we know what the size of all of our directories are, we can run through them, look at the total size of the directory, check for the ones that are under 100,000 or under or equal to 100,000, which is the condition we were given in the problem, and total them up. So like normal with these problems, once you get through figuring out how to parse it and compute what you're after, actually getting the answers out is not so bad. So let's jump into the next process next command function, because that is probably the most complicated part of this, like parsing out the results from the shell output that we've been given. So let's start with that. So this function could almost be recursive. We can see that it's taking an iterator, a reference, and the directory to work in. So it looks almost like we could call it again, but you've got to be careful with that because the input we're given actually goes quite a few levels deep in directories, and you end up blowing the stack if you try that. So as it stands, this just about works. If you try and add any calculations in here, it falls apart. So not a good idea, don't do it. Yeah, so iterators, so effectively this does one step in an iterator. So it'll pull something out of the iterator, do something with it, and then return so that the function can be called again. So the first thing we do is grab something off the iterator and pull out the first few characters. So 2 through 4 ignores characters 0 and 1, so we ignore the dollar and the space. 2 through 4 is grabbing characters 2, 3, and not 4, because it's exclusive on the upper bound. So that's grabbing out the command from that line. And then we can match, so we can say either it's a cd command, an ls command, or we don't know what to do with it, and we'll just panic. So if it's a cd, then we grab out the directory that we're cding into. So that will be characters 5 and onwards. So it'll either be something like a slash, or the name of a directory, or it'll be ... to go back up to a previous directory. So exactly like cd would behave in a normal shell. So if it's go back, then we're using the built-in path handling for Rust. So we're saying take the current working directory, pop one value off it, which means just remove the last element. So we go back to the parent directory, and we return that. Otherwise, if it's not a go back command, if it's just a go down a level to a new directory, then we join the current path to the new path name that we're being given. So that would be the situation like we're already in /abc, and we do a command like cd into ctz, and that'll take us down a level. So rather than doing all the string handling for this ourselves, just easier to use the built-in path handling in Rust. And although we could just do this and assume that every single one of these names is unique, it's probably best not to. So yeah, I've gone with absolute paths to directories as we go. So that's our cd. Then if we get an ls command, we take the directory we're currently in, and we're going to try and look for all the output for that directory. So that would look like this here. So we've done an ls command, we get back some output for it. So that is all the directories and the sizes of the files in there. So we can't do anything like assume that those are files. We are being told that this is the format. Just so things with extensions aren't necessarily files. We've got some things without extensions. So yeah, we have to parse that format properly. So that is the next job, is to try and work out whether we've got a dir telling us it's a directory or a number. So we do the same trick as we did with finding the command. We try and grab out, I'm going to come back to this in a second, we try and grab out the first few characters. If it's a directory, then we treat it as a directory. And we do, again, the same thing. We join the path to find the child directory name. And then we push that child into our current directory so that we know that we're going to have a child size to resolve later. And then otherwise, if it's not a dir command, or a dir marker for a directory, then we're going to find the size. So we just split up the size space file name, and we parse that as a number, and we keep track of how many files there were in that directory, so what the content size was. So the bit I've skipped over here is how we're knowing when to stop. So the way that the ls command works, it will print out some content for us, and then we'll return to our shell prompt to be able to type in the next thing. But we don't want to consume that from our main iterator, because that would mean that we'd have to somehow backtrack or pass forward the thing we accidentally consumed. So what we've got here is a peekable iterator. So the peek just lets us look at the next value. So we're saying, give us the next value back from the iterator. If that starts with $1, then we stop. Because we processed all of the output from ls, we want to stop, go back to our top level loop, and call this function again to start processing the next command, which should be a cd. So that pretty much explains all of that. And then the last little bit here is just dealing with, once we've found our result from the ls, we store it. And there's just a quick check here to say, if we do a replacement by accident, if we've not built a correct path name, so that we have two directories that we think we've calculated the children for, but we've actually ended up making a mistake with our paths and we've clashed, the insert function will return the old value. So it should return none every time here. But if it returns some, we're going to panic just to make sure that we've got a clean solution here that's pushing new values into our tracker. So the next thing I want to look at is this type, this dir content, because that's not standard library. That's something I've written. So let's go to that next. So I've started by putting this inside a module, and that is just a Rust feature of the language. So this dir content is a public structure, or it's public at least within this module if we were to put it at the top level, within the main module. And if we did that, we'd be able to see these properties of the struct, and we'd be able to write to them, read them, and we wouldn't be forced to use the structure properly, use its implementation. So by putting it inside a submodule, we're able to separate it out properly and use it as it's intended, rather than sneakily accessing its internal properties. So the implementation for this structure gives it some behavior. So we've got a new function, which is effectively like a constructor in other languages. So it's a way to build the struct with default values. So it's just a function that returns type self and builds a struct. Then we have some methods that give this thing behavior. So we're able to add to the self size of this directory. So the self size is how many files do I contain? What size does that add up to? So every time we find a file, we can call this function. So that we've already seen. We can add a child. So every time we find a subdirectory, we can push it into here so that we know when we come back later to compute the total size of this, what directory sizes we need to look up to figure out how big this directory is in total. Then we can get an iterator back over all the children. So that we don't need yet. We'll come back to that. We have this isLeaf function. So this is checking for directories that don't have any children. So this is directories that just contain files, which will be useful later as a base case when we come to traverse the directory structure looking for total sizes, because we'll know when we can stop when we reach the bottom of the tree and we have something we can just calculate without needing to know what child directories are. So that's useful later. We can also write back the child size. So once we've computed what the size of all of the children directories are, we can write that back into this so that we can store it and reference it later. So that's just probably not something you would want to do in like production code, but it's a useful way to keep track of this so we don't have to recalculate it every time we want to know it. And then the getTotalSize function will return us the self size if it's a leaf. So as I was saying, if we don't have any subdirectories, then we can just get our own size and we're good to go. Otherwise, it returns the total size if it's calculated. So if we haven't pushed the child size in yet, and this isn't a leaf node, then we won't know what our size is, and it'll just return none, which is the default value. Otherwise, if we've pushed in the child value, then it'll return it properly. So there's a onus on us to use this type properly, otherwise it won't behave as we expect. But that's okay, because it's a fairly small program, and it's just there to solve a challenge. So let's go and look at the next piece, which is using this structure to compute the sizes of the directories all the way down the tree. So this is the last big piece now. So compute child sizes. The job of this function is to start from a given directory, and for our program, we're just always going to start at root, and it will work its way down through the directories to figure out what the directory size you've started from should be, and it'll figure out, as it goes, all the child directories that it has to touch. So by scanning the root directory for what size is that, it's forced to scan all the way down and fill in the sizes of every directory in our file system. So has a bit of a side effect, but that's okay. So we start by grabbing the dir content, the structure we've just been looking at, for the directory we've been asked to find a size for. If we already know its size, we can just return it. So that will usually only be true for a leaf node. But if we were to call this function again, or if we were to call it in like two different parts of the tree, this would eliminate the need to recalculate. And then once we've got a situation where we don't know what our child size is yet, we've got to calculate it. So we grab our dir content and borrow. So this is important. We're using a ref cell here. So this is the point where this got introduced. It didn't really make sense to add it any time before this. So until I got to this point, this was just a hash map mapping from string to directory content, with a string being the absolute path to that directory. The ref cell is here so that we can mutate inside the hash map. So the compute child sizes needs to be able to both pass a reference to the directory sizes down recursively, and also modify, which it does in a moment, the size of the current directory. So we wouldn't be able to do that if we didn't use this ref cell. So what the ref cell lets us do is say, I know that I'm only going to access this mutably once at a time. So lots of things can read it, only one thing will write to it, and it's up to me to write a correct implementation of that. If I don't, it's checked at runtime and it should fail. So we get an immutable reference first. We grab the children, so that's calling a function on our struct, which gives us back an iterator over all the children in our directory. We map each child by computing the child size, and that's where we go recursive. So the child path becomes our starting point, and we'll look at its children and its children all the way down to the leaves, which is our base case for this recursive function. Once that returns, it'll give us back a size for that child. We sum all of those up, and then we borrow our directory content mutably and push the child size onto it. So once that's set, we don't need to do any work again. If we were to call this function again, it's now filled in. Getting_total_size will give you back a value. So we're effectively filling in our tree so that we can use it to solve the problem in a moment. So that is that function. And the last piece is to quickly summarize what the final step is, and then we can go and run this. So just as a quick reminder, now we've been around this loop of understanding what the other functions do in here. we can have a quick look at what we do last. So we take the filled in directory sizes. So now we have our tree, and all the way down it, all the subdirectories have known sizes. So we take the values, which is the directory contents of the hash map. We map that by grabbing out the total size, and we know that's filled in now, so we're just going to unwrap that optional. Then we filter for values that are less than or equal to 100,000 in size, and we total that up. So that's just what the problem was asking for, and that should hopefully be the answer to part 1. So let's go and give that a test. So let's run this twice. First time, I want to run it with the input that we were given on the challenge, just to check that we've done something sensible. It's a fair bit of code this, and it would be good to know that we're on the right track. So I've got that set up initially. Let's cargo run this, and we're going to get an answer of 95437. So we'll remember that and check it in a second. And then if I put the input file back to what it should be, and then we'll run it again, and we get 1449447. So let's go and check if that's the right answer. The answer we got by running the sample input was 95437, and that is indeed the right answer. So that's promising. We're at least doing something sensible, even if we haven't covered every case. So let's try putting in our answer and see if that's right. Fantastic. So the work was worth it. We got it right. Let's start part 2. Part 2 looks much friendlier. So we're being told that we've got a certain amount of total space on the file system, and we need that much free space, which is just under half of it, to do the update. So the idea is to free up some space, and we're being asked to find one directory that we can delete that will free up enough space. And because there are multiple options, like we could just delete the root directory, we're being asked to find the smallest directory that we can delete to free up enough space for the update, and then we're being asked what's the size of that directory. So that sounds like we can just run through our directories, work out how much space we save if we delete them. If it's enough, we can keep that one, and then we can find the smallest of those. So let's give that a try. I've copied in the constants that we've been given in the exercise, so 70 million units file system size and 30 million units required space for the update. So from that we can start working out how big a directory we need to delete. So first thing we care about is how much space we're already using. So we can do that by getting our directory sizes, grabbing the root directory, which will tell us how much space is used by the entire file system currently. We can unwrap that because that's an optional on the get. We need to borrow to unwrap the ref cell. Then we can get the total size of that directory, and we can unwrap that as well. That's optional, but we know because we've already run through all of these and unwrapped them that that's safe to do. So let's go ahead with it. So that's our current used amount. Then from the current used, we can work out how much space is free, which is the file system size, take away what we're using, that's how much is left over, and then we can work out how big a directory we need to delete. So then directory size will be the amount of space we need, take away how much is free. And we'll assume that the inequality is the right way around for these because we're being told that there's not enough space on the file system. So we'll assume that required space minus current free is accurate. That tells us how much more space we need to get to the update being able to run. So then from there, we can work out how much, or which directory we need to delete even, like find the size of the directory that's bigger than the min size, and pick the smallest of those. So let's take all of our directory sizes, we'll grab the values, which gives us back the ref cell dir contents, not keyed by path anymore. We'll map those, and we'll take a dir, and that will be dir.borrow. It'll take a second to work out the types, so we'll just hope and get total size, and then unwrap that. So it'll give us back all the sizes of directories. And let's see if we can improve things here by giving this a type. This will be a reference to a ref cell of dir content. There we go, that cleans up the errors, makes it a bit easier to work on. Then we can filter the directories that are not big enough to be usable. So we require that the size is greater than or equal to the min size. Min size. Let's save that to format it. There we go. And then we can find the minimum value. So if we do min by, and we can compare two sizes. Let's call that x size and y size. And we can just call compare on those two. X size and y size. So that'll be a built-in comparison for integers. We don't have to write that ourselves. And then we can unwrap the result. And that should give us back the thing we're after, which is the smallest directory that's bigger than the min size. So let's see if that's the case. Result. And let's then print that out. So we'll print line. And let's print a bit of extra information here. So we'll say the file system is currently using that much. And we need to free at least this much. And we've selected what directory. So let's add those things in. So that'll be current used or current used min directory size that we can have. And then result should just be the number we've picked, the size of the directory that we're going to delete. So we don't know which one it is the way we've coded this, but we know what the size of it is, which is what we need to answer the question. So let's run that and see how it does. Right, what do we get if we run this? So warning for an unused import, that's fine. And then we get a funky looking output. So we're saying we found a surprisingly small directory. We've got a negative number, which we didn't expect any of these to be. And we've also got an amount of size that the file system is using that looks way too low. So the file system is 70 million units. That is 27 million used. So there'd be enough space for the update if that was true. So we've got a bug in here somewhere. I'm going to go hunting, and I'll get back to you in a minute when I've got an idea what that might be. Okay, so I think I found it. So we've got an extra bit of code here now, which is tracking the total amount of size of directories. So every time we find a directory, we'll only see those once because we're traversing the tree exactly once. So I'm keeping track of that, summing it up at the end. And when I run this, it comes out with 48 million used out of 70 million. So that starts to make some sense. That doesn't leave us enough space for the update. So that looks like it's good. So I think the parsing is okay. The problem then must be something to do with the compute child sizes. So what are we doing in here? We are running through directory sizes. We grab the directory that we've been asked to find the size of. We compute its child contents, which goes and grabs all the sizes of child directories. And then we return that, which tells us how big the child directory was. The bit that's missing is exactly here. So that's not the right thing to return. What we actually care about returning is how big is this directory plus its children. So that's actually easy to get once we've put the child size onto here. So we can just do bm, and then we can get total size from that and unwrap it. And that looks a lot more sensible suddenly. That is giving us back the combination of the two. So the files in our directory plus the ones in subdirectories. And that would explain why we were missing like 20 million units on our size. So let's try that and see if it behaves any better. Okay, second time lucky. Let's give this another go. Cool. So we're seeing the 48 million used space now, which is much more sensible. We need to free, what's that, 8 million? And we've selected something that's 8.6 million. So that seems fairly sensible. It's bigger than the min size, which makes sense. We wouldn't necessarily have a directory of exactly the minimum size we need. And it's bigger, so I'm convinced. Let's go and give that a try. So total size for the directory we're getting rid of. Is that right? Awesome, it is. I hope you found this all right. It was a little bit of a different format by going through the code rather than just live coding it all. But let me know if it was good, if it was not good. And hopefully you got on well with this problem. And I look forward to seeing your solutions on Reddit.